the reporter for the sovereign opponent.
We challenge problem number 9, mathematics.
Number 9.
Rejected.
Rejected. Okay, so
We challenge number rotated. Number 7, rotated.
okay, number 7. Okay, rejected. So number 9 and number 7 rejected.
Number 15. Valuable.
Okay, rejected. Number 15.
We change from number 2, your loss.
Okay, number 2.
Sorry.
So reject 2. So Team Su, you know you can only reject 5 problems, right?
Yeah.
Okay, so let's continue. Just remind them.
We change from number 4, time back.
Sorry, we only have
No, yeah, just reject ourselves.
reject.
Then
Disqualified, right? No. They just minus some points, but not.
okay, so number 4 rejected. So continue.
I'm sorry, can we see like what question?
No, just ask, just challenge. Just challenge.
We change from number 11, spring research.
11, problem 11.
Yeah.
Reject. Okay, so 11 reject. So continue. You got 4 more.
We change from number 5.
Number 5,
Reject.
reject. Okay, number 5 reject. Okay, so continue. No, just challenge.
No, there's a fun. So when we have only 5.
Just continue. That's all the problem available. So unless
No, when there's only 5 choices, like fewer than 5 choices, that's the
Yeah, sure. So please see the. Yeah, there's still some problem. Does that answer?
we have
1, 3, 6, 13, 14.
we change from number 3 as well.
okay, number 3 accept. And the reporter has 1 minute to prepare. Okay, so the reporter, opponent, and reviewer on the board, write your name. Okay, reporter takes the floor.
I am the reporter today for Power 3 Lato. Overview. Concept will contain how Lato start, how to convert a vertical force into a horizontal force, coefficient of restitution, small angle simple angle period formula, problem statement. Attach a bolt at each end of a string and connect the center of the string to a pivot. When the pivot oscillates along the vertical direction, the bolt starts to climb and oscillate with increasing amplitude. Investigate the phenomenon. Experience setup. We pass the scale with 5 centimeters in the wall to use tracker. And pass stickers in the table to make sure the camera is in the same place. And make the camera and the wall parallel and make a distance with 2 meters. Experience method. We record the video and use tracker and Excel to analyze it. Experience method. Our ball one is 7.7 gram and one is 0.8 gram, and its radius is 1.5 centimeter, and string's length is 20 centimeter. Concept. Initial speed is necessary to start Lato movement. Without a gap, the oscillation never begins. Initial speed is necessary to start Lato. You can see my hand This is how vertical force turn to horizontal. This is from the perspective of force. This is tension force of the rope. This is gravity. So it will be a horizontal component. And this is from the perspective of energy. And this is gravity. And when it falls, it will become kinetic energy. Potential energy became kinetic energy. Like this. Mgh become half mv squared, and when it climb, became half mv prime squared and become mgh prime. This is U1. U1 and U2 is initial speed, and V1 and V2 is final speed. And if it is elastic, and M1 equal M2, and V1 equal U2, and V2 equal U1, and if U1 equal U2, then V1 equal U1. But in lateral case, it is inelastic. So U1 equal U2, and V1 equal E1. This E is coefficient of restitution. And when this equals 1, and when it hit together, it will return to the same place. Concept. This is initial height, and this is final height. And V1 is final height, right? Final speed, and this is initial speed, and this alpha is coefficient of restitution. And Mgh become half mv squared multiply alpha squared, and become half mv1 squared become Mgh prime. So h prime equal alpha squared h. This is one impact, and h double prime equal alpha squared h prime. So alpha squared h. So this 2 is number of impact. So it becomes like this. This is time, and this is period. So like this. This is fitting line. And we'll get this. Concept. This is simulation, and when E equals 0 to 1, it is inelastic, so it will be forced oscillation. As you can see, its height is almost the same. And this is region 2. But it is E coefficient of restitution equals 1. So it is elastic. In theory, it might be distinct bit node, but it doesn't. It also forced oscillation. We think it might be when my spring be tightened, it will be some energy turned to the heat. Data analysis. We use different from the height point and the lowest point, and get the jewel that my hand made. As you can see, my standard deviation is so low, so I think it is accurate in analysis. This is fitting line, and with my lateral being a high place and my hand don't move, so it will be decayed, so can get this line. Data analysis. This is theory. My length is 0.2 and gravity is 9.8. So period is 0.89. But in practically, 0.83 subtract 0.4 multiply 2. This and this is the time that two height planes. Because when it entered, this is is a period. The lateral swung here and back to here. So its period needs to subtract 2 height points and multiply 2. And use this, so I can get the coefficient of restitution of the 2 balls. It is 0.91 and 0.89. These 2 times is come from here. Conclusion. Initial speed is necessary to start Laplace movement. With the gap between 2 balls, the oscillation can start. Calculate the period using the small angle pendulum formula and derive the coefficient of restitution through the kinetic to potential energy equation. Estimate the energy input from the head during stable oscillation and plot in a breaking line. Thank you.
So that's it. Okay, so the opponent has questions. 2 minutes.
So I'm the reporter, I'm the opponent from TYPT. So first question I want to ask is that can you again explain your experimental setup? Because I cannot hear the performance.
Okay, please project your voice.
Can you again show your experimental setup in your first pages? Yeah, can you explain it again?
Okay. I place a scale with 5 centimeters like this. So I can use tracker to measure. And use stickers, paste stickers in the table so I can make sure camera is in the same place. And make the camera and the wall parallel. And the distance is 2 meters.
So is the ball colliding while touching the ball, or is it touching the wall?
No.
No. Thank you. So, is there like later experimental analysis? Are they from your simulation or your experiment?
Use the geomet I can make.
Like your analysis on your data. Yeah, this is
Not simulation.
This is from experiment.
Yes.
Okay, so do you consider the lateral as a 3D or 2D motion?
Maybe 2D.
So do you consider the work done by hand? Can you show it? Like, because it's you say it's a forced oscillation. Because it's a forced oscillation. So can you see where you consider the work done by hand?
Okay, hands up. So the opponent has 3 minutes to prepare. Okay, the opponent makes for 4 minutes, then discussion.
Good morning, honorable judges and fellow contestants. I'm the opponent from Team West. The problem I'm going to pose today is problem number 3, lateral. So let me restate the problem statement. So we attach a ball to each end of the string, connected with the center of the string on the ball with a pivot. So when the pivot oscillates along the vertical direction, the ball starts to collide and oscillate with an increasing amplitude. So later on, we'll investigate the report investigated this phenomenon through how did the lateral start and how the energy is transferred in this oscillating system. So so in their phenomenon, they say that the vertically oscillating pivot, so have with 2 balls, and the ball will start colliding, like in their experiment. So in their theory, so they say that you need an initial velocity to begin this oscillating motion. Also, the initial speed is important. Also, they say that gravitational energy transfers to kinetic energy. And also, they say that this system is a forced oscillation, so the hand does work to this system. In their experiment, they use Tracker and Excel to analyze their simulation or their real-life videos. And they didn't change any parameters, they fixed it. They use hand to oscillate and they observe the amplitude and the period. Okay. So first the pros, they clearly demonstrate the phenomenon using like videos, and they include and also they have a clear explanation of the experimental setup. But however, I think their experimental accuracy is concerning because they use hand to oscillate this system. Also, they lack error bars and they misuse the small angle formula. So later on, I would like to discuss the following points with the opponent. First, I would want to question whether they can confirm that this system is a 2D motion because they show no evidence to prove that there does not exist a 3D one. And especially when they use a tracker which only tracks the 2D motion. Also, they didn't consider the slack of strings in their simulation. The slack here means the softening of the string. It's not always tight. Also, so in their theory, they use the period equals 2 pi times the square root of L over G. However, this is only usable when the angle is small. And in their simulation, I can see the angle is almost 90 degrees, so I cannot see how that can be used in this system. Also, in their energy, and also I see that in their lateral simulation, with the same oscillating hand, the ball eventually goes to the same frequency. So I would want to ask how the energy distribution happens in that system. Also, other discussion points, especially about the experiments, I would like to ask the concerning accuracy of using hand and whether they attempt to use error bars in their graph demonstration. So now I would like to invite the opponent up to the stage to discuss. So can I use the board?
Sure. Please project your voice. So
Yeah. So as you can see, if you use a tracker video to film the lateral, you see its motion in the plane. However, I can see that in your video that the lateral may be fluctuating like this. So this velocity projected to this plane will not be the exact velocity. How do we
make sure that is parallel to how did you see?
Because if you just use it casually by hand, you cannot make sure that it always collides. The first point that it needs to collide at the center, like this center. Second, it needs to be a 2D motion. You cannot say you observe it because if it's me, I would suggest that we can use a camera here in this plane to check that if it's really 2D motion that we have assumed. And I think that is a very important thing because that really matters when you are calculating the velocity of the system.
In experiment, I call it a string.
before the freeze face the
Sorry.
yeah. So project your voice.
the string like this, and I hold in this place. So I think it will parallel to the wall.
Yeah, I think that can prevent something, but if you really want to check it, I think we're using a camera to look at it. Okay. So the next question I want to ask is, have you ever considered the slacking of the string in your simulation? Because in your simulation, I think you set your lateral to be a light stick, am I correct?
I see.
That cannot bend and does not have any weight.
We think it will be tight.
Throughout the whole system, like throughout the whole oscillation?
No throughout all situations. Maybe in the time I pull up big line.
Yeah, I totally agree. So when you lift up your left lateral, the string tightens. But when it's oscillating downwards, like this, I think the string will actually get soft. So in your simulation, I think you assume that the head is doing positive work when it lifts up and doing negative work when it goes down, right?
Yes.
However, the negative work doesn't happen because the string is soft.
I don't know.
So I think this is the point that you need to adjust your simulation. Because simulating is very good because you don't need to conduct the experiment. You have a very good, precise simulation. And I also suggest that if you have a good simulation that you probably have made, you should use that to change more parameters. You can change the length of the lateral, like not only constricting to your experiment.
Because that simulation is just to told you that we count when e equals 0 to 1 or equals 1, it both are forced oscillation. That simulation is just to tell us.
Yeah, so I think you need to modify your simulation because it does not really conform to the reality. Okay, so the next question I want to ask, because the period is a very important factor dependable factor that you observe in your experiment, right?
Yes.
You compare the different lateral experiments through the period. So it is important that how you define this period and calculate it correctly. So if you use that function that I have talked to you before, there will be a lot of issues, especially when the theta is like 90 degrees. The error will be tremendous. Because if in the real world, we need to write this equation using Taylor expansion. So there will still be a lot of angles here. And when the sine theta equals to 90 degrees, these can grow huge. So that will lead to a very big period deviation.
As you can see, this is theory, and this is practical. It's so similar, right?
What's your theory? Your theory is this, right? So are they similar? So I think, yeah, you should do some, I think you could modify your theory because this is more precise, especially in this kind of big angle oscillations. So the next question I want to ask is about the energy distribution. Oh no, I think you don't understand what this is. I want to ask how the energy flows in this system. So you say that in a normal pendulum, the gravitational potential energy transfers to kinetic energy. But however, this system is a forced oscillation. So work does positive work, but does not do negative work here. Right?
Can you speak again?
The hand inputs energy into this system. Right?
Yes.
But you say in your simulation that the energy seems conservative. It's not, the ball is not dividing like higher. So how can you explain this? you think they're mainly they're just because of the damping?
You say my handmade works to labrados
Yes,
and
yes. Like your hand consistently puts work into the system, but the system's energy stays conservative. So that means there must be some factor that you're missing. For example, damping. So, but I don't think that damping accounts for that much of energy loss.
you think that the string will be tightened. We think the string will be tightened. So it, my hand material is like string. My hand material will echo that string tension. String tension dual.
So I think the main, so I didn't really understand. Can you say that?
You just said I make job to laterals, but it's almost the same height.
Yeah.
So you asked me why it won't be higher and higher.
Yes, yes. And that is actually the problem statement. That is oscillate fast.
Because we think my hand material is equals the tension of the rope. It will tighten, and when it tighten, my hand material is equal to that. So it won't be higher and higher.
So I think the main issue is that you calculated the negative work done by hand, and it's going downward. So that means you're stable. Because according to your theory, if the hand is consistently inputting energy into this system, it needs to bounce higher. And I don't think that the E is so big to cancel out all the work done by hand. Okay, so I have to read one question. So I want to ask about your accuracy using hand. Because you cannot fix your frequency. Like in your simulation, it's fixed frequency. And you can also not control your force.
You can see my high point subtract noise point is almost the same, and you said frequency is very similar.
So, so from observing this, I think that you have a very stable hand movement. That's very good. But you can further improve it through a mechanical linkage like this. You can use the rotation of this thing to convert, to make this an even more stable oscillating system. And that is going to improve your experiment.
Maybe the machine will be not so accurate.
I think that's more accurate.
Okay, time's up. The opponent summarize the discussion. 1 minute.
So in the discussion, we talked about whether the lateral system is 3D or 2D motion. So ideally, it should be 2D. So I think in further experiment, they should prove that it is 2D through a lateral camera. So make sure that it doesn't oscillate over a certain small length. Also, they didn't consider the slack of strings in their simulation, and that actually leads to the miscalculation of their energy flow in their system. Also, in their theory, they mainly use the analysis of T, the period, lateral. But they misuse this small angle formula of period. And in my opinion, they should use the big angle formula, Taylor expansion. Also, we talked about the energy flow in this system, and this is referring back to the schematic sheets. Also, about the accuracy.
Okay, time's up. The reviewer asks questions.
So, do you think the tracker video is an accurate way of measuring the experiment?
Can I start first? So I think tracker is probably the only way in this experiment, but I do know that it's like inaccurate. If the FPS are too low, or you just track by hand.
Do you think the tracker video is an accurate way of measuring the experiment?
Yes. Because I can check the locus of the ball.
So you mentioned that about the slack of the string. So in your theory, do you think the slack of the string is negative?
You say I can ignore the slack of the string. Maybe yes. Maybe yes.
Okay, so I have another question for the reporter. So you mentioned that low standard deviation means high accuracy. Are you sure it's not high precision?
I think it's accurate.
And you mentioned the three-dimensional movement. How significant do you think the three-dimensional movement will be on the?
Please protect your voice.
How do you think the three-dimensional movement will be significant on the theory?
Just like I talked about the three-dimensional movement that causes the real velocity to be projected onto the tracker 2D motion, and that actually severely affects your E calculation, like because you need the first enter speed and eject speed. That is a very big problem.
Right. You've also mentioned mechanizing the lateral experiment.
Yeah.
How do you think we can account for the amount of energy we need to start the oscillation? Because once you start, you have to lower the frequency to make it go higher.
Lower? I think higher. I think frequency needs to go higher for the oscillators. Frequency needs to go higher for the balls to collide higher.
So you think the frequency has to change in the mechanizing?
Yes.
So do you think that hand is consistent enough for the data to be usable? So you use this small angle here. What angle do you think is the maximum for the small angle approximation to do that?
I think conventionally 5 degrees would be below 5 degrees would be appropriate. In lateral, I can see that they bounce like almost already over 90 degrees.
What do you think the maximum angle for this?
Actually, our angle is just like this. Inspiration is
Okay, time's up. And the reviewer has 2 minutes to prepare. Okay, the reviewer takes the floor.
So I'm Byron, and I'll be reviewing the lateral question. So the problem statement states that to attach a ball to each end of a string and connect the center of the string to a pivot, and when the pivot oscillates along the vertical direction, the balls collide and oscillate with increasing amplitude. It's a investigative phenomenon. So their main focus was on the starting phase of the lateral and the vertical force to horizontal force conversion in the small angle single pendulum formula. So the reporter, they mentioned that when the two balls moved up and down, they have initial speed, and within initial gap, they would oscillate. The theory is that they have to calculate the gravitational to kinetic energy transfer, and also calculate the velocity of the ball after the collision, assuming that the energy is conserved, and they also simulated the phenomenon. In their experiment, they compared the track motion of the lateral to the simulation, and they measured periods of undriven scenario. And their conclusion was that there was an initial energy needed to start the lateral, and some pros of the reporter's performance was that there was a clear layout of presentation. The simulation and experiment visuals were clear, and they spoke at a reasonable pace. However, they didn't have the slide numbers page, so it made it harder for us to keep track of what they're talking about. And their experimentation is mainly done to analyze the base case, not the whole phenomenon. And they mistook accuracy for precision because standard deviation measures how close the data points together, which is precision. And the opponent's performance, they emphasize the theory errors, slack and large angles and issues like the slack in the string and how the small angle pendulum doesn't account for large angles. And they brought up errors in the experiments from hand and 3D motion. And they had a strong, clear voice, and they emphasized clear flaws in theory. And their cons were that the time allocation for the experiment, the time to talk about the experiment was lacking. And they brought up the problem focus, but doesn't emphasize the key parts, from gaining amplitude. And they didn't understand the reason for a small angle. Now, moving on to the discussion. The opponent mentioned that they use track video to film the motion. There will be a fluctuation between the z-axis, and that the exact velocity can't be determined due to this error. And the reporter responded that in the experiment, they hold on to finger in parallel to the wall, that it doesn't really matter if the fluctuation of the z-axis. But the reviewer agrees with the opponent because the fluctuation of the z-axis is inevitable and result in different energy distribution. And then the next question, the opponent discussed the slack of the string. They believe that since lateral is a light string and can't bend no way, the string should soften on the down motion, so there should be no negative work since the string is soft. And the reporter thinks that it will be tight, not throughout the whole simulation, but only when you lift it up, so it's negligible. The reviewer agrees with the opponent that there will be no negative work since the string is softened as you go down. And then the next discussion point, the opponent discussed the different lateral experiment, comparing different lateral experiments to the period, definition of period, accurate calculations in small angle, and the small angle pendulum now being applicable to larger angles, and to use circular expansion instead. The reporter had an unclear answer, but then the reviewer believes that the single pendulum theory only has a 10 to 15% error due to the Taylor expansion. And there was a lack of, the opponent, they said that there was a lack of understanding in the energy distribution of the system. The normal pendulum from gravitational potential energy to kinetic energy, the system does force oscillation.
Okay, time's up. The reporter makes the final remark.
Though using machine, don't be 100% correct, but maybe accurate. shown by the handle. Conclusion. Coefficient of restitution the gap between two balls and the initial speed.
Okay, so then time for question from the jury. So any questions from the jury?
What are the key factors to say that are the loss for the system?
I think it's
The tension of the string.
yes.
Okay.
The key factor of the loss of energy, I would think it's the the ball goes down.
Okay, project your voice, please. Project your voice, please.
I was thinking it's the driving support as the ball goes down the pendulation.
You mean with the particle will spin?
I think the torque is negligible. I think the main factor, apart from inelastic collision, is the huge vibrating of the string, and that can be clearly seen in the phenomenon.
Okay, so question for the reporter. In your simulation, first of all, all simulation shows that you getting bigger and bigger. Anything change, just the program running, make it bigger and bigger. The vibration of the ball. It looks, in the end, they go all wild.
Yes, it will be the same.
So there's no change in the parameter, you just run the program, it will go like that.
Yes.
So in your simulation, you use force, or you just plug in the formula for a simple pendulum. So when you write a program, in your program, when you calculate the motion of the ball, you use force, F equal to MA type of simulation, or you just plug in the simple pendulum formula, which one you use?
I don't know what to.
Like you calculate the force and then get the acceleration, then you move the ball in the program, or you just use fixed formula to predict what the trajectory will be.
Use
So you use the force. 0.89 and 0.86, how different is that? For review, that's all.
I think 0.89, 0.86, that's 0.03, and that is about 3%.
So you think Tyler seems space is necessary?
I think because there are like a lot of deviations in their simulation, so with everything tumbled together, that is like the only 3% deviation is only like an accident.
Okay. So for all of you, even let's say the collision is 45 degrees to the camera, would that affect the estimation of E in the experiment? E is the ratio of the two velocity changes, right? So if 45 degrees, would that affect
Oh, sorry, I want to, can I correct myself before? I think it will not change the calculation of E, because it's all like cosine like 45 degrees.
You?
I also don't think that will affect the E because Foster goes with higher amplitudes according to the hypothesis.
All right. You?
Can you speak question again?
So let's say your camera is placed wrong, so the ball is climbing like this way, like your camera is facing. Would that affect the calculation of E in your experiment?
You use the coefficient of restitution
Right.
by measure.
Right. No, estimation of the coefficient of restitution in your experiment.
You say is it accurate or?
Will that affect the result for the measurement of E?
The camera's angle will affect E.
Will that or not?
No.
And
How do you think about the influence of the velocity and acceleration of the pen or the machine taking the velocity?
Because if we increase the amplitude, then the frequency will change as well. Because if you make it too large, the bars will be slower on the downtake.
I think if the hand's acceleration or like restraints and velocity increases, then the work input into that system is more. So that will lead to the amplitude like gradually increasing.
More questions? Okay, then time for the grade. Okay. Here we declare the grade. Okay, so the number for the reporter, okay, 75435. And number for the opponent, nine, 6, 7, 8, 6. And number for the reviewer, 5, 6, 7, 6, 6. Okay, so comments or sorry.
For the reviewer, please show it again.
Oh, sorry. Okay. 5, reviewer, number for reviewer. Five, 6, 7, 6, 6.
Okay, thank you.
Okay, so comment for the reporter from the lowest, Professor Duan.
You're going to try your best to do this variable, but actually there may be more variable with your influences. Maybe you can only do the good situation, but like at least at a simulation problem, you continue to example the P-roll oscillation frequency and to see what happened to this. And I think for the presentation, the key is the time management, because you finish your report at about 8 minutes, so I think you still 4 minutes time for you. So instead maybe there's more work you can do for the experiment.
Okay, so for me, about 7, first the presentation is clear, and the result is somewhat not clear because when you show the data, it's not clear. You show the result from simulation or the experiment, the reviewer, opponent actually knows. I agree with Professor Duan, but since the clarity and also your response to the discussion, I think it made the whole game much more interesting and inspiring. So that's why I give you extra points. I was giving you lower points, but in thinking the response, I give you more points. That's my comment. Others? Okay, so comment for the opponent, again from the 6, any suggestion or comment? No? And me, I give the high points because the reviewer has a very good points. Although I don't totally disagree every single point he made, but he made the points and he lead the discussion and he tried to make sure the reporter understands the question and whole discussion is fluent. And it opened another point for follow-up thinking. Okay, experience is not great, but the discussion is great to me. Okay, so I think it's very inspiring for the leading discussion. For reviewer, so, any comment for the opponent? No, then for the reviewer, Professor Chen, the highest?
Their statements are clear to me, and I thought at least they have pointed out main issues and important issues. Yes, so that's why I give 7.
Okay, and 6 or 5, I think about the same. 6 or 5. Any comment from 6 or 5? To me, you do a fair job. That's it. Okay, so you follow and you catch the key point, but it's not clear to me you will help or bring up or more your view. So that's up to you. Okay, so that's the end of the game. So we'll move on to the next stage after 15 minutes, right?
Yeah.
Yeah, 15 minutes. Okay, so.